be having our morning keynote address delivered by Dr. Max Holmes. Dr. Holmes is an Earth system scientist who studies rivers and their watersheds and how climate change and other disturbances are impacting the cycles of water and chemicals in the environment. He is the director of the Arctic Great Rivers Observatory, the Global Rivers Observatory, and the Cape Cod Rivers Observatory. Dr. Holmes is also interested in the fate of the vast quantities of ancient carbon locked in permafrost in the Arctic, which may be released as permafrost thaws, exacerbating global warming. Dr. Holmes has ongoing projects in the Russian, Canadian, and Alaskan Arctic, and in the tropics in the Amazon and the Congo. He is committed to engaging students in his research projects and to communicating the results and implications of his research to the public and to policymakers. He previously served for 2 years as director of the National Science Foundation's Arctic System Science Program, and in 2015 was named National Fellow of the Explorers Club. We will also be having a Q&A session after the talk, so please feel free to use the link projected on both sides of the screens to submit any questions you may have for Dr. Holmes. So please join me in welcoming Dr. Max Holmes and his morning keynote address.
Thank you very much for that introduction. Thanks for the beautiful music that preceded it. And thanks to all of you for getting up early and coming here on this beautiful Saturday morning. I want to talk for a couple of minutes right at the start about where I come from, the Woods Hole Research Center. And raise your hand if you've heard of Woods Hole. So, you know, I don't know, 10%, 20% have heard of Woods Hole. And that's maybe about the right percentage around the world if you go and ask if people have heard of Woods Hole. But most people think it's all one place. I thought it was all one place before I arrived in Woods Hole 20-some years ago. But I'm just going to give you a quick sort of history of Woods Hole. So if you go back to 1888, the Marine Biological Laboratory was founded. They're still there. Just a few years ago, they affiliated with the University of Chicago. But MBL has been there since 1888. In 1930, the Woods Hole Oceanographic Institution was founded. They're the guys with the big ships that travel around the world doing oceanographic research. In 1975, the Ecosystem Center was founded at the Marine Biological Laboratory to study Earth's ecosystems. And then in 1985, the guy who founded the Ecosystem Center, George Woodwell, left and started the Woods Hole Research Center. So that's where I work now. I previously worked at MBL, and I'm also connected with the Woods Hole Oceanographic Institution. But the key point is that these are independent research organizations, all in this small village of Woods Hole, which is in Cape Cod, Massachusetts. At the Woods Hole Research Center, our focus is on climate change. And we do two things. One, we do sort of the underlying science related to climate change, how the Earth's systems are changing as the Earth is warming, how that can feed back to influence climate change. But we also work really hard to connect the science to policy, to hopefully shorten the gap between the research and its application for what we would hope would be wise public policy. And I think it's that combination of attributes that for the last 4 years in a row has gotten us named the world's #1 climate change think tank. I don't think of us as a think tank at all. I'm not even quite sure what a think tank is, but we're pretty happy to have this recognition in any case. We work around the world, studying how the Earth's system is changing as the Earth is warming. And we try to go to the hot spots where the changes are the greatest or where there can be the biggest feedbacks to climate change. So these are just some of the programs that we focus on. We do a lot of work in the Arctic, and I'll talk a lot about the Arctic in today's presentation and why that's important. We work a lot in the tropics. We think about the carbon cycle globally. Increasingly, we're thinking about extreme weather and risk associated with that, whether it's storms, hurricanes, extreme rainfall and floods, fire, drought, all those kinds of things, and what that means for all of us. And we also work on rivers around the world and coastal zones. So I'll touch on several of these aspects during today's presentation. Some of you will recognize this person, Kate Shafer, and this sort of explains how I ended up here today. So Kate is a teacher here at Harker. In the summer, she goes to Woods Hole and teaches at the Woods Hole Science School. And it was, I don't know, maybe 4 years ago, I was giving a presentation to her class about much of the stuff I'm talking about today, probably. And we started to talk after that and stayed in touch. And I think a year later, she went with me to Alaska and helped out with the science that we do there. So this photo was taken in the Yukon River Delta in Alaska. So thanks to Kate for getting me connected with this wonderful school. And it's certainly a testament to this school to have teachers like Dr. Kate Shafer here teaching the students. All right, so I'm going to talk today about climate change at the start, some general discussion about climate change. Then I'll move to the Arctic and why it's a particularly important region with respect to climate change. And then I'll talk about rivers, and I'll try to wrap all these things together. Who knows what the Keeling Curve is? Few hands go up. So Charles David Keeling was a scientist at the Scripps Institute of Oceanography in San Diego in La Jolla. And in 1957, he started measuring carbon dioxide in the atmosphere. That measurement has been going on since then, and it's an incredibly powerful data set of how the Earth is changing. But it's essentially a typical graph that we're all used to seeing, and this is sort of my take on that. So what I'm going to show are a series of photos, and below the photo is the date the person was born, and on top of the photo is the carbon dioxide concentration in the atmosphere when that person was born. So this is my great-great-great-grandmother. She was born in 1820. The concentration of carbon dioxide in the atmosphere when she was born was 284 parts per million. My great-great-grandfather, born in 1847, carbon dioxide, same concentration. We know these concentrations not because somebody was measuring them at the time, but we can go into ice cores, collect gas samples, air samples that are trapped in ice core, and reconstruct the carbon dioxide concentration in the atmosphere at that time. And in fact, you can go back the previous 10,000 years, again, through analyzing gas trapped in ice cores, and carbon dioxide never varied much from this 280 or so parts per million concentration. Sometimes a little bit less, sometimes a little bit more, but no big departures over that 10,000 year time period. So this is my great-grandfather, born in 1873. Maybe it starts going up a little bit. My grandfather, we're up to 297, so we start to see an increase. My mother, who turned 80 yesterday, 311 parts per million when she was born. When I was born, 320. And here's my son. You see the big jump. My daughter, who's in the front row, 387. And today we're at 412. So what you see is essentially these first 3 generations, essentially no change in the carbon dioxide concentration. The next 3, we were going up at about 3 parts per million per decade. And then we get this big jump of 20 parts per million per decade increase or something like that. So the big question is, what happens moving forward? Does the carbon dioxide concentration in the atmosphere continue to increase? And of course, carbon dioxide is the main greenhouse gas, the main heat-trapping gas. So what happens to carbon dioxide is what happens to Earth's climate in short. Does it keep going up? Does it level off? Does it go down? And the answer to that question depends on several things. One, it's where do we get our energy? Do we rapidly switch to renewable energy sources, wind and solar, things like that? This is an aerial shot of part of the Woods Hole Research Center where I work, where all of our energy comes from wind and solar. Or do we keep relying on fossil fuels, coal, oil, and natural gas? And when we burn these things, we're putting more greenhouse gases into the atmosphere. It also depends how we treat Earth's ecosystems, Earth's forests. So this is a shot of the canopy of this in the Amazon, just a continuous coverage of trees, of forests in this part of the Amazon. And when I took this shot, we were in a small plane a few miles away. This is what it looked like. So this is a field that was cleared to grow soybeans. There's 1 tree left in the field. It's a Brazil nut tree, which is protected, so they could get rid of everything else, but clear the rest. And if we would have been there a few years before this photo was taken, this would have looked exactly like this. So they came in, cleared the trees to grow soy. Forests store vast amounts of carbon, so do we maintain forests? Do we restore forests? It has big implications for the future of climate change. And it also depends on what happens below our feet. So this is a shot that was taken in the Yukon River Delta in Alaska, where I was with Kate a few years ago, and we go there every year. And below our feet is frozen ground, permafrost, sort of permanently frozen ground. And I'll talk about why that's really important with respect to what happens as the Earth starts to warm. This is another shot of permafrost. This is along the Kolyma River in the Siberian Arctic, up near the Arctic Ocean. And you can kind of see below my feet the sort of shiny area. That's just frozen ground. It's what's called an ice wedge. It's essentially ice has been frozen in the permafrost. In this case, the stuff's been frozen for about 20,000 years. And one of the ways we know it's been frozen that long is each time I've been here, when we walk along the beach at the sort of the base of this eroding cliff, you find bones like this. So these are bones of mammoth and other long extinct animals. You can radiocarbon date those bones. And in this case, you find they're roughly 20 to 30,000 years old. So this ground has been frozen for 20 or 30,000 years. Now it's starting to thaw and erode. And it's important because of all the massive amounts of carbon that's locked up in that permafrost. This is at that same site, zoomed in, and you can look closely, and I think you can probably make it out in here in this soil. You can see roots. So in a tropical or temperate region around here, if a plant dies or the root dies, that root rapidly decomposes. But in the Arctic and permafrost regions, because it's frozen away, you get much of that material is preserved. So in fact, these roots, small, fine roots, are 25,000 years old or so. That's been preserved for that long, but as the permafrost is starting to thaw, as the Earth warms, that material starts to decompose, and in the decomposition, it releases carbon dioxide and methane, which are greenhouse gases and cause more warming. This map shows the distribution of permafrost in the northern hemisphere, so the different shades of purple are different categories of permafrost, but the important thing to note is that about a quarter of the northern hemisphere land area is underlain by permafrost. And when you think about what's going to happen to permafrost and all of the carbon it contains moving forward, one of the important things to recognize is that warming is accelerated in the Arctic. So the warming in the Arctic is about twice as high as the overall average global warming. And this map is just showing the temperature anomaly or the change from the mean, with the redder colors being where the warming is the greatest. So at the top of the figure in the Arctic regions, you see the warming is greatest there. These are model predictions, scenarios for what may happen to permafrost over the remainder of this century. This is sort of near surface permafrost, the upper few meters. It shows the permafrost extent and how that may change over the future based upon different scenarios of how much greenhouse gases we're putting into the atmosphere. But you can see that even in the best case scenario, the projection is that we'll lose about 30% of the near surface permafrost over the remainder of the century. And a worst case scenario, a sort of a business as usual scenario, is that we'd lose about 70% of the near surface permafrost. So even the best case scenario is not too good. We're going to lose a lot of permafrost moving forward. So you get global warming, which is causing permafrost thaw, but the arrow, as I've suggested, also goes the other direction, where permafrost thaw can feed back to amplify global warming through the release of carbon dioxide and methane, two greenhouse gases, as that permafrost thaws and its carbon decomposes. Okay, this number, 2 degrees Celsius, has gotten a lot of attention in the international climate negotiations, and the thought was that in order to avoid the worst consequences of climate change, we should limit total warming to no more than 2 degrees Celsius. In fact, more and more we're recognizing that this 2 degrees C threshold is too high. Maybe 1.5, or certainly 1.5 would be a lot safer. But for the numbers that I'm going to show now, I'm going to use this 2 degrees C threshold. All right, so the question, how much carbon can we emit if we're to remain below that 2 degrees C threshold for average total global warming? And the numbers I'm going to present are in billion tons of carbon released. And so it's about 790 billion tons of carbon humanity can release and to stay below 2 degrees C threshold. We can emit no more than that if we're to stay below that 2 degrees C warming. It seems like a lot. It's a hard number to wrap your head around. It seems like a really big number. But the bad news is that number, that's since the start of the pre-industrial period, say roughly 1850. And we've already emitted about 570 billion tons. So that means we have about 220 billion tons left to go if we're to stay below that 2 degrees C threshold. Okay, how much carbon is in different pools on land or in the ground that could be released? forests. All the vegetation globally, which is mainly in the Earth's forest, holds about 500 billion tons of carbon. Fossil fuels left in the ground that we could get to if we continue down that road, so that's coal, oil, and natural gas, contain about 1,200 billion tons. And permafrost, frozen ground in the Arctic, has about 1,500 billion tons. So it doesn't get nearly as much attention, but it's a very big pool of carbon that could be released as the Earth warms and permafrost thaws. How much carbon could be released from thawing permafrost? This is a sort of a best estimate. Over the remainder of the century, around 130 billion tons of carbon could be released from thawing permafrost under a sort of business as usual scenario. So remember, we have 220 billion tons to go. Half of that, roughly, could come from thawing permafrost in the Arctic, the decomposition of material that's been frozen away, locked away in permafrost. And most policymakers haven't really recognized this. They're focusing on fossil fuels and what we can do to limit greenhouse gas flux emissions from fossil fuel combustion. They're thinking of vegetation and forests, what we can do to limit greenhouse gas emissions from deforestation, for example, but they haven't focused so much on the permafrost part of the story. So what needs to be done? There's always more science to be done to understand how quickly permafrost will thaw, and when it does thaw, how quickly it will decompose and release greenhouse gases, and also whether those greenhouse gases will be emitted as carbon dioxide or methane. You get a lot more warming per carbon atom if it's released as methane instead of carbon dioxide. So the ratio of carbon dioxide to methane emission is really important in figuring out how much warming will be caused. But we also need to do a lot more in communicating the science to policymakers, to voters, to everyone, so that hopefully we'll do a better job of tackling and solving this problem. And I just wanted to point out a few ways that we're trying to do that. Things like right now, talking to all of you about this. We have a book in the works that will talk about our work. This is just a draft of the cover of that book that will talk about the work we're doing in the Arctic on permafrost. That also involves undergraduate students from around the country and around the world. And that will come out sometime this fall. There was also a recent, couple of weeks ago, story on 60 Minutes that featured these two Russian scientists that we worked closely with, and it talked about their idea, something that can be done in the Arctic to help keep the ground frozen. So it was this permafrost focus. So I'd recommend this to you if you want to. It's online. You can check that out, and we helped out with that story. And this morning before I came there, this caught my eye in the New York Times. So this is an article in the New York Times that's talking about a project that we're involved in at the Woods Hole Research Center, where we're doing the climate science and working with partners in the financial industry so that they can better value the assets that they control. And our hope is that once you better account for climate risk and asset valuation, that will be a big lever for tackling climate change. And I'll admit I haven't even read the article. I just quickly grabbed this shot from it. But this is a wind turbine on the right, a wind turbine at the Woods Hole Research Center. And on the left is a map of the site, one of the sites where we work in the Yukon River Delta in Alaska, and where we take a group of undergraduate students each year as part of what we call the Polaris Project. All right, now I'm going to shift a little bit and talk about rivers. All right, so what is a river? Now, pretend you all have a box of Crayola crayons and a sheet of white paper, and you have 30 seconds to draw a river. So just imagine what you're going to draw with that crayon and that sheet of white paper. I'm going to pace around for a minute while you think about what you're drawing. All right, I've asked each of my kids to do this in the past. This is a photo of my daughter, I don't know, 5 or 6 years ago, something like that. And this is what she drew. How many of you drew a sort of a curved blue line mentally? And I've done this actually in classes with paper and crayons, and 90% sort of draw something that looks about like that. And I think that's really good. This is a map. This is a Congo River watershed. The black line's the outline of the Congo River watershed. The blue line is the river. And this was done by a guy named Greg Fisk, the senior geospatial analyst at the Woods Hole Research Center. He's a map maker, and he drew something really close to what my daughter drew and what probably many of you would have drawn. This, you know, curved blue line, maybe with a branch or two coming off it. But now I just want to zoom in on part of this watershed. And if you look closely, what you see is that there are river channels intersecting with the landscape on a much more fine scale. So it's not just this one or two, you know, the main channel and a tributary, but in fact there are smaller rivers interacting with the watershed, the landscape, much more intimately. And you can kind of make an analogy with sort of the human circulatory system. So on the left you see, you know, some of these big veins and arteries that get all the attention. On the right you see a zoom in on the capillaries where you have vessels that are intersecting with every cell in your body. And in some ways, that's the way river networks work. There are these big channels that make it on the map, but there are smaller channels that interact much more intimately with the land surface. And we can take this analogy a little bit further and think about, so when a physician collects a blood sample, it's not that they're so much interested in your blood per se, but they're interested in what they can learn about the health of the individual based on the chemistry of the blood. And even more importantly, maybe what they can learn, if you get your physical every year, they look at how your blood chemistry changes from year to year, and that gives them clues about your health and how that may be changing. And the work that I do much of my work focuses on similar things, but with river water samples. So we collect river water samples from around the world. We do that over time, multiple times a year, and hopefully many years. And we look at how the chemistry of the river changes. Again, not because so much that we're interested in the river per se, although in many cases we are, but even more so, we're interested in what we can learn about the health of the watersheds, the land draining into the rivers, based upon the chemistry of the river and how it changes over time. All right, back to this blue line that my daughter drew, and some of you may have drawn. Let's think about that color. So these are some samples that we collected throughout the Congo River watershed in the main channel and a bunch of tributaries. And what you see is not really so much blue, colors that range from more or less clear to brown. And that color is the color in the river water. What you're looking at is dissolved organic carbon. And so the darker color has higher concentration of dissolved organic carbon. You can think of that as tea. So essentially if you're making tea and dropping a tea bag in there, you're leaching dissolved organic carbon from those tea leaves. And in fact, you can do some fancier chemistry and try to figure out where that carbon came from that's in river water. And most of it comes from not material that's generated within the river, but is coming from the surrounding watershed. Again, making that link between what you see in the river and what's happening in the watershed. So that carbon's coming from vegetation that grew on land and then leached into the river. So the key thing to think about is that, you know, the chemistry and discharge of rivers integrates what's happening in the watershed. So sort of armed with that knowledge, where would a guy like me want to go and start collecting river water samples to see how things are changing? And my answer to that, my first answer to that was we want to go to the Arctic. And the reason we want to go to the Arctic, I've already said, things are happening quickly already. Warming's about 2 or 3 times greater in the Arctic than it is globally, so that's where the biggest climate-related changes are happening. It's also, it's a relatively small ocean with lots of big rivers dumping into it. So if you're interested in how land and ocean interact, as we are and colleagues are, we want to go there as well. The Arctic has about 10% of global river discharge, so global river flow, and it's going into about 1% of global ocean volume. So that land-ocean connection is stronger in the Arctic than anywhere else. We've already talked about how much carbon is locked up in permafrost. It's roughly twice as much carbon in the permafrost in the Arctic as is in the atmosphere right now. And also, it's a relatively understudied region, so there hasn't been a lot of work up there, so there's a lot of work to be done. We know it's an important place, and there's a lot of fundamental work that remains to be done in the Arctic. So back in the early 2000s, we put proposal into the National Science Foundation to fund some work that we wanted to do on the largest Arctic rivers, tracking how their chemistry and discharge is changing over time. And that project is still going. We call it the Arctic Great Rivers Observatory. We work on the Arctic's 6th largest rivers. So the colored regions that you see up there are the watersheds of these 6 largest rivers. So it's 4 of them in the Siberian Arctic, the Ob, Yenisei, Lena, and Kolyma rivers in Russia, and the Yukon and Mackenzie rivers in North America. And in each of those rivers, we go down near the mouths of the rivers where they dump into the ocean, and multiple times a year collect water samples and track how the chemistry is changing. So this figure just shows the hydrographs of the seasonal discharge. So this is actually plotting daily discharge of each of those rivers, and the dots on those graphs are the days that we have collected water samples. So again, you can see we started in 2003. We're still going in 2019, and we hope to keep this going so that we can continue to track how things are changing over time. One thing you'll note is that discharge varies greatly over the course of a year in these rivers. So in the winter, which would be like right now in the Arctic, discharge is very low. So there's still water flowing down the river, but it's very low. But when spring comes, and generally late May or early June, all the snow melts and you get these big discharge peaks. So we've really focused on sampling at all these different times of the year, again, to get a handle on how the chemistry is changing, and then to think about what that means for how the watersheds are changing. Just a little bit about some of the logistics. This is on the Lena River in the Siberian Arctic, and this is a boat that we use for sampling on the Lena River. This photo was taken back in 2003 when we were just getting started. And on the boat, we chartered this boat for 2 weeks, and there were 3 American scientists, 3 Russian scientists, 6 crew members sort of running the boat. And it was in August, and the captain of the boat brought along his 13-year-old daughter, Anya Soslova. And the first few days, she was kind of shy, and as we were sampling, she'd just sort of watch what we were doing. And then eventually I'd sort of, I didn't speak Russian. She didn't speak English at that point, but I would call her over, and she'd hold on to a water bottle as we were doing our work. And after that, every time we'd stop and sample, so she'd be there and helping us with the sampling. And when I was forgetting a step or something, she'd tap me on my shoulder and correct me. And somewhere along the line, I had the thought, at that point, we weren't going to be back to this region for 6 months. But she lives right beside the river. Her father's the captain of the boat we use for sampling, and we had a bunch of extra water bottles. And I explained to her through a translator that, if she wanted to stay involved in the project, that'd be great. If she didn't, that was fine too. But I left her some bottles and said, if you want to fill some bottles while we're gone, fantastic. And it turns out, we didn't hear from her for 6 months, but it turns out that every 2 weeks, she was out there collecting water samples through the winter. This is just a shot of one of those times that she was out there collecting water samples. It could be minus 50 degrees, and she'd be out there collecting these samples. So that was just this fantastic addition to the data set. It kind of grew to involve not just her, but her classmates, and then we tried to replicate this involvement with schools at the places around the Arctic where we were working. And this is fast forward to, this was last summer in Alaska. This is Anya, who was that 13-year-old girl. She's now a research assistant at the Woods Hole Research Center and continues to work with me on this project. And her father is actually the guy who's collecting water samples still on the Lena River in Siberia. All right, just a couple of sort of key results from this project to date. One of the important things that I haven't spoken too much about discharge, but we find that the discharge, the amount of water flowing down these rivers, is increasing. It's about a 10% increase we have some longer-term records for discharge that certainly predate when we started working on these rivers, but there's a lot of extra fresh water flowing into the Arctic Ocean from these rivers that influences the salinity of the ocean water, which influences the density, which influences the circulation, and that can all feed back to climate. So that's one of the important stories. Another is that the chemistry is changing. So river chemistry changes seasonally a lot. It changes from year to year. So you have to do this for a while to be able to detect a long-term signal, to be able to see that long-term signal. And we're now starting to see that. And most of the chemical constituents that we're measuring carbon, nitrogen, phosphorus, all different kinds of things, we're starting to see a signal of change. And so the scientist in me gets really excited about that. It's sort of what we've expected that we were going to see. But then I also step back and think, God, this is actually really a bad thing. This is not what we want to see. You know, it just shows the magnitude of the changes that are happening in the Earth system when you start to see it in the chemistry of these remote but large Arctic rivers. And another sort of, I think, key result is that we think we're starting to see the carbon getting older in the river. So we measure the age of the dissolved organic carbon in the river water, radiocarbon date that, C14 date that, and what we've expected to see as the permafrost thaws, it starts to release the old carbon, and we think we're now seeing that. And again, that's one of those things that the scientist in me gets really excited about. Every other part of me is like, this is not good. We want that permafrost to stay frozen, and we want the carbon to stay in the rivers, or stay in the ground, but we're now starting to see that signal of change in the chemistry of the rivers. All right, so I've talked about this Arctic project a bit. This has been going since 2003. Where do we go next? Where does our mind go when we start to think about what else we might want to do to capitalize on the power of rivers, river chemistry and discharge to tell us something about how large regions of the Earth are changing? We started this project that we call the Global Rivers Observatory. So in addition to the Arctic rivers, which are shown there, we're going to other big rivers around the world to do similar kinds of things, to look at how the chemistry and discharge is changing over time. And I'm just going to show a few slides, talk a little bit about this project. It describes some of the places where we do some work. This is the Amazon River in Brazil, where we sample. This is at a place called Observatory, which is the sort of the downstream-most place where discharge is measured on the Amazon River. Just a little trivia for the day. To equal the discharge of the Amazon River, you have to combine the discharge of the next 9 largest rivers on Earth. So the Amazon is just absolutely in a class by itself in terms of the size of the river. This one river alone has almost 20% of global river discharge. So this is where we sample. We've been doing this since, I think, 2011. This is a shot. This is also in the Amazon, and you can see the water that's sort of milkier, and then the darker water at the bottom. So that milkier water is Amazon River water, and the darker water at the bottom is a tributary of the Amazon coming in. So that Amazon water has lots of sediment in it that's coming from erosion in the Andes mountain. The tributary flowing in, this is a Tapajos River. It's draining a rainforest area, relatively low gradient, very little sediment, but lots of dissolved organic carbon. So this just kind of visually shows how the chemistry of river water can give you clues about the watershed, what kind of watershed it's draining. This is just a shot from the Congo River. And one thing, I guess, when I got into science as a kid, so the age of many of you probably, I never sort of, I always loved science, but I never really imagined sort of the adventure that science could be and the places in the world that science could take you. And I guess it never ceases to amaze me, just some of the places I get to go to do the science that I do. And certainly in the Congo, we've gotten to some just incredibly remote areas in the Congo, and it's just striking, like, how did I get here? But it's a real privilege to be able to do it, for sure, and it's really neat to think about where science can take you. All right, I've spent sort of much of my career and much of my time working on these big rivers around the world, and I've sort of ignored the rivers, the smaller streams and rivers closer to home. But recently we've started to work on rivers on Cape Cod, which is just sort of out my back door. And I'll just talk a little bit about that. And it's been a lot of fun. So this is Cape Cod. This peninsula sticks out into the Atlantic Ocean. It's about as far from here in the US as one could possibly be. And when one thinks of Cape Cod, what gets all the attention are the beaches and the ocean and the coastal zone. But we do have some water quality problems there. The estuaries are impacted by nitrogen inputs that's coming from land, and much of that's coming in through the rivers. And to my surprise, I said I've sort of ignored the rivers on Cape Cod since I've been there. I learned that really nobody was doing this kind of work that we're doing on rivers around the world, right in home on Cape Cod, and looking at how the chemistry is changing over time and thinking about what that means for the health of our estuaries and coastal waters. So we started doing some of that work. Again, collecting samples. We're doing this, it's easier to get to these places, so we're actually collecting samples every week now on, I think it's 9 or 10 rivers on Cape Cod. This is just one of the rivers. I mean, these are much smaller systems, but locally very important. These are the places we're sampling. And this is just from the website. This is sort of a screen grab. This is nitrate, so this is a nitrogen compound, and it's the thing that most directly is influencing the water quality, the sort of the estuarine health. And you can just see how, number one, we're making these samples at very high resolution. You can see how rivers that outwardly look very similar to another in a very small area on the Cape, you can get very big differences in nitrate concentration. So we're interested in, we want to keep this going over time, see how things change over time, hopefully put pressure on managers to figure out ways to reduce nitrogen concentrations, reduce nitrogen inputs to the coastal zone. But until now, again, nobody's been doing this, so it's hard to say how things have changed over time. So we're going to try to keep this going and keep an eye on these river systems. You remember a few slides back, I showed that shot of the Amazon and Tapajos rivers and how they looked very different. These are just filters. So these are filters that we use for filtering the water samples that we analyze. These are from the Cape River. So the rows are 6 different rivers that we sample on Cape Cod, and the columns are different weeks. So it's just like a time series of filters, and this is a photo of these filters, and you can see, very clearly the color varies among the different rivers, and the color doesn't show up so well. Some of these are really green, that second row. Some are brown, some are light. You can see that the rivers vary from one another, and you can also see the rivers change over time. All right, where do we go next? We work a lot in the Arctic. We work on some of the big rivers globally. We work on rivers on Cape Cod. What are we thinking about next? And I'm just going to highlight 3 projects that are either just getting started or just sort of churning around in my head right now and think about where we're going in the future. One I'll mention is a partnership with some of you guys here. So Kate Shafer and some of the students here have started to sample the San Pedro River, and I'm excited about that. Those water samples will come back to Woods Hole. We'll do some of the chemistry there. Some of the analysis, I guess, will be done here. And I think there's the potential for that to grow and maybe include some other rivers. My daughter and I, a couple of days ago, checked out the San Pedro for the first time. So yeah, it's a beautiful spot to do some of this work in this region and keep it going and see how the water quality, to see how the health of these watersheds is changing over time. I'm also really excited about this idea. So to go to some rivers in areas where the permafrost may be rapidly changing. And the site I'm thinking about is in Alaska. There's a series of 7 watersheds. These are rivers sort of intermediate size. So they're not these massive Arctic rivers where we do much of our work, but they're also not these really small systems on Cape Cod. They're of a size that one can sample throughout the river system over a, say, 2-week float down the river. And so these 7 rivers, the watersheds on the southern end, they're all kind of side by side by side. At the southern end, there's essentially no permafrost. At the northern end, it's predominantly permafrost. And in the middle, it's in the middle. But they're all rapidly changing. Unfortunately, probably 50 years out, I'm not sure there'll be much permafrost left in any of these. But I want to start this similar kind of work where we're looking at the chemistry and how it's changing over time in these watersheds, in these rivers with rapidly changing permafrost. And we'll have our first trip, our first sampling on one of these rivers this summer, where 11 of us will float down. It's the Queethluck River, and it's the one with a lot of permafrost right now. We'll put some sensors out that will be making some measurements when we're not there. We'll collect samples from the main channel and the tributary, and then the plan is to get back there next year, and as well as some additional rivers, and start to make these measurements. And again, eventually we'll build up to, I hope, these 7 rivers in Alaska. And finally, the project that I'm thinking about right now is what I'm tentatively calling the Mountain Rivers Observatory. And instead of going down near the mouths of rivers as they're dumping into the ocean, where the signal you see is the signal of everything that's going on in the watersheds, which may be direct, it may be climate change signal, it may be sort of direct human impact, agriculture, or whatever. I'm interested in going up sort of high in the mountains in isolated watersheds where essentially the only human impacts are going to be indirect through climate change, or there won't be agriculture, there won't be deforestation, there won't be those sort of direct human impacts. So we're sort of scouting out some sites in the Rockies. We're going to scout out some sites potentially around here where we can get pretty high up in watersheds and again look at what should be a relatively pure signal without direct human impacts, but more any changes that we'd see would be more likely just a climate signal. And with that, I'll wrap it up and entertain questions.
So now we'll be having the Q&A session. Our first question is, why do you think that scientists have been unable to connect with the public on climate change, and how would you fix these communication issues?
Well, it's a great question. It's a really challenging question. Why haven't we done a better job of connecting with the public on issues related to climate change? I don't really have the answer. I think one of the challenges is that roughly, well, prior to 10 years ago, you could get folks from sort of across the political spectrum recognizing the science and that the climate was changing and that we needed to do something about it, and it wasn't polarized and it wasn't political, or it wasn't partisan. Certainly the solutions are political, but it doesn't need to be partisan. But then 10 years ago or so, there was a divide. It became a very partisan issue, and we know what happens when issues get really partisan. Not that much happens. Why that happened is hard to say. How to overcome that is also a challenge. And I mean, I think there are encouraging signs recently. The conversation, they're encouraging and discouraging signs. But I think people are I think maybe the bad news is that it's starting to become obvious enough that more and more people are seeing it. It's harder and harder to deny the science, and thus people are recognizing that something needs to be done. You certainly see it in California with fires and drought, and this is happening kind of around the world, that the impacts of climate change are becoming more and more obvious. There will and should be discussion and argumentation about what to actually do about it. There are lots of good ideas that can come from all different places about how to tackle it, but I think it's getting harder and harder to deny that climate change is real and that humans are the main driver of that and that we need to do something about it.
Thank you. Our next question is, what, in your opinion, is the cause of the unfortunate politicization of the scientific issue climate change?
Yeah, so I kind of jumped the gun on that one, but yeah, I mean, maybe a little bit more about the cause. One thing that I thought about as potentially one of the causes for the polarization. I mean, it's got to be a political, the solutions have to be political, but it shouldn't be polarized. It was back in 2007 that the IPCC, the Intergovernmental Panel on Climate Change, won the Nobel Prize and shared it with Al Gore. So Al Gore was a sort of leading the charge in communicating issues related to climate change. At that point, I thought that was a great thing. In retrospect, in some ways, I think that was a terrible thing. And I think it was a terrible thing in that, not that Gore was saying anything wrong, but he was a very polarizing figure. So we've interacted a lot with this guy named Bob Inglis, and he was, as he put it, he came from the reddest district of the reddest state. So he was a congressman from South Carolina, and when he talks about climate change back when he was in Congress, he said all he needed to know about it was that Al Gore was for it, so he was against it. And I think a lot of people were like that, and so I think that was part of the polarization. He then, I think it was his son, became of voting age and said, you know, Dad, I agree with you on a lot of issues, but I think you're wrong on climate change. So this guy, Bob Inglis, did his homework. He went to Antarctica. He interacted with some scientists. He studied. He accepted the science. He recognized that things were changing. And then he made a terrible career decision. And when he was campaigning for re-election, he said, yeah, climate change is real and we're the cause and we need to do something about it. And instead of winning in a landslide, he lost in a landslide. He didn't make it through the primary. And I think that sort of sent a chill through a lot of folks in Congress. I think there are a lot of people in Congress that recognize the science, but they know that they're unlikely to get through the primary if they kind of get out, if they say too much about it. So yeah, how do you salve it? I'd like to think that a lot of people will do what Bob Inglis did and sort of study it and recognize the science. I think that will happen in some cases, but I think in a lot of cases it may be that the Earth will be changing so rapidly that it just kind of hits you in the face and you say, my God, this is real. We better do something about it.
Thank you. Our next question is, what can each of us do to counter misperceptions about climate change, and how do we have a dialogue with climate change deniers?
Yeah, how do you talk to people who have different views than you do? I think one is you don't get into an argument. You're not going to make any progress if you just sort of dig in your heels and say you're wrong and you're foolish to think these things. I think what I like to do, and number one, I like to get in places where people have different views. I think a lot of times we kind of live in our bubbles. In Woods Hole, I live in a bubble and I interact with scientists and everyone kind of thinks like I do about climate change. I think it's important to get out of your bubble, talk to people who have different views, and then have honest discussion about those views. And I like to go back, take a few steps back to where we all agree and kind of walk through and try to figure out where we diverge. So like some of the stuff I showed today really can't be argued with. The concentration of carbon dioxide in the atmosphere, I don't think anybody's going to argue that what I showed was wrong there, that, you know, 100 some years ago, carbon dioxide concentration was 280 or whatever, and we've kind of, it's gone up, and we're up at 410 right now. I mean, that's just fact. There's no room for argument there. You can't really argue that carbon dioxide is a greenhouse gas and it leads to warming. It's really hard to argue where that extra carbon dioxide came from. We know. We can kind of do the math. And so you walk through all that. And then where people maybe diverge, I think they diverge about what we should do about it. They diverge about exactly what the future is going to look like. The future is always hard to predict. But yeah, I guess what I try to do is take it back a ways, and you recognize, look, we agree on a lot of things. We can disagree about the political, what we should do, you know, should it be tax credits, should it be a carbon tax, should it be this, that, or the other, that's all legitimate policy debate. But where I don't think, I'd like to get to the point where we're not arguing about the fundamental science. And I see some signs that we're getting there.
Mm-hmm. Thank you. Our next question is, what is your view on electric cars? Will they have a meaningful impact on climate change?
Yeah, it's been really exciting to be out here just the past couple of days and to see all the electric cars. They're far more prevalent here than they are on Cape Cod. I mean, you certainly see some and it's increasing, but there are a lot more here than where I typically am. I think that's encouraging. I think it's fantastic. I mean, it's sort of the next question is, where does the electricity come from that's powering those cars? And there we need to do more. You know, it only does so much good if you're not getting that electricity from renewable sources. But certainly wind and solar are rapidly expanding. And I could have shown a graph that's really encouraging about the rate at which wind and solar energy is expanding. And it's just skyrocketing. And yet I could show the next figure, and I've done this sometimes, where it shows the percentage of our energy that comes from those renewable sources like wind and energy. And it's still a pretty minor component, with fossil fuels by far the biggest source of our energy. So we need to get off fossil fuels. The electrifying transportation is a really key means for doing that. If our cars and vehicles are all powered by gas and diesel and so on, it makes it an awful lot harder. So yeah, congrats to all the people out here that are doing a lot of that work that makes it possible.
What can we do in our daily lives to reduce our impact on the environment?
Great question. So what can we all do? You can think about what you eat. That's one. Even before that, I mean, some of the low-hanging fruit, food waste. Food waste is an enormous amount of energy goes into producing food, and an awful lot of, and greenhouse gas is associated with that, and a lot of that food ends up in the trash. So just doing things like reduced food waste is something that all of us can do that will really make a meaningful dent in climate change. You can also think about what you eat, and things have different sort of greenhouse gas climate impacts based upon what you eat. And I'm not going to say everyone get off meat and become a vegetarian, but we can all take a couple of steps down that chain, eat less meat. That makes a big impact. And you can also think about the meat that you do eat. And I didn't recognize this until recently, but if you sort of compare the climate impacts of, let's say, chicken or pork to beef, like beef is in a class by itself in terms of negative climate impact. So eating less beef and moving down that food chain is a big thing. You can talk to people, and this gets back to sort of the earlier conversation. I would advise, not to argue, not to say, you're foolish to think these ways, but figure out a way to have a sort of honest conversation about people, and again, think about what you agree on, what you don't agree on, and try to bridge that gap a little bit. Vote. Many of you are not at voting age yet, some are, but yeah, that is incredibly important. And I say this not to say who to vote for. I would hope that whoever you vote for, you're asking them, and whatever party they're affiliated with, you're asking them to recognize climate change, our role in it, and our responsibility for doing something about it. And that's also an incredibly important thing, I think.
Mm-hmm. At this point, do you think it's possible to stop climate change, and why?
Yeah, is it possible to solve it? I think the gap between the best case and the worst case scenario is huge. In any case, we're going to feel some impacts of climate change moving forward, but it's in our control to influence how big those are. So sort of on a business as usual scenario, it doesn't look good at all for the future. If we aggressively tackle it, yeah, it's going to be manageable. We're having impacts right now. They're going to get bigger, but if we aggressively work to solve it, we're going to minimize it moving forward.
Is there any scalable synthetic way to remove carbon dioxide from the atmosphere?
Removing carbon dioxide from the atmosphere. Yeah, it's not enough just to put less in. We actually have to figure out how to pull some out. There are some pretty easy ways of doing that, like plant a tree. Photosynthesis is when plants grow, when they photosynthesize, they're pulling carbon dioxide out of the atmosphere, storing it in their body. So that's a good way. There are other ideas like ocean fertilization, ways of, that's also photosynthesis related. So increasing biological productivity, pulling carbon dioxide out of the atmosphere. There are people working on things they call direct air capture. These are technological approaches to pulling carbon dioxide out of the atmosphere. I don't know so much about that. I think there's potential. I mean, at this point, the energy required to do that is very high. It's not scalable at this point. It's not to say that at some point in the future that may be a big part of the solution, but we're not there yet, and it's certainly not, in my view, something to bank on and to say, well, technology is going to solve it moving forward. Hopefully it's going to be part of the mix. It could be a big part of the mix, but we're not at that scale yet by any means. We don't have that solved at this point.
Have there been any recent government policies about permafrost?
No. No, there haven't, and there's, permafrost is different than, say, the other two big sources of greenhouse gases to the atmosphere, fossil fuel combustion and deforestation. So one can make policies about those two things, but there's the carbon release from permafrost. There are no really direct controls from that. The permafrost is thawing as the Earth is warming. The main contributors to that warming, again, are fossil fuel combustion and deforestation. So there's little that we can do directly in the Arctic to keep permafrost frozen and keep that carbon in the ground. So the controls are really, really elsewhere. And what we've hoped to do with sort of trying to get the permafrost story out there, including to policymakers, is to give them extra motivation to control what they can control fossil fuel and deforestation in order to help keep the permafrost frozen. That 60-minute story that I alluded to features this Russian scientist who has an idea about a sort of Arctic-based solution for keeping permafrost frozen. And I'm sort of in the interest of time, I don't think I'll go into that too much, but it's kind of a crazy, interesting idea, something that, an experiment that he started in the Arctic to help keep the ground frozen.
How can we create the diplomatic capital to address climate change on a multinational scale, especially in light of the US pulling out of the Paris Accords?
Yeah, great questions. We certainly, I think, ceded our leadership on this, in this area when we pulled out of the Paris Climate Agreement. Other countries, I mean, part of the good news is other countries are stepping in and taking over a leadership role. So I think China, for example, was acting quite aggressively in a positive way to combat climate change. There's still a lot more to be done, obviously, but as the US has sort of stepped back in the last couple of years, I think other countries are seeing it as an opportunity to become global leaders in this area, and they are doing that, and there are good things about that. I'd say in terms of the US role at the federal level, it's discouraging in my view right now, but projecting, you know, I think it's not going to be too long into the future, in my view, until you're not going to get elected as president of the United States without saying that climate change is real, that humans are the main driver of that, and that we need to do something about that. And I think that's, and then I think the U.S. will, at that point, become a leader once again. I think, and I'm pretty encouraged that that's going to happen soon. One, I think, case study or place to think about is Florida. So Florida, as many of you probably know, has lots of electoral votes. It can go either direction in terms of the major parties, and it's kind of in the epicenter of climate change impacts through, you know, sea level rise, through hurricanes, things like that. It's becoming really hard for anyone living in Florida to deny that climate change is real and that we need to do something about it. And it's also, if you want to become president, you need to work awfully hard to win Florida. So I think we're really close to the point where you're not going to go to Florida and campaign as president without, again, acknowledging climate change. And I think when that happens, that changes sort of politics nationally. So I'm optimistic that the U.S. is, at the federal level, will assume a leadership position again quite soon. I would say that in the absence of leadership in the federal level, states are stepping up, towns and cities are stepping up, businesses are stepping up. So there's a lot going on in the U.S. still that's encouraging. It's just at the federal level that is, I'd say, discouraging.
Great. Thank you so much for this engaging Q&A session and for your fascinating talk. Hopefully this inspires us all to take action.
Thank you. Thanks very much. Thank you.